is a Bernoulli process, Bernoulli trial, right?
Yes, yes,
So,
it is a
sir,
Bernoulli.
when we sum up these Bernoulli trials, we get a
Hmm,
binomial distribution, right?
correct.
So, sir, then what is exactly the Bernoulli process? Like we are summing it, and we are already binomial distribution is there.
No, no, no. So the Bernoulli process is basically this Z1 through Zn that I defined, right? Z1 through Z1, Z2, etc. So IID tosses that result in a Bernoulli process. Okay, it's as simple as that. Okay, don't get bogged down with the names. So Bernoulli process means you take a coin, toss it. If it is head, you write one. Otherwise, you write zero. Toss it again, head or tails, one or zero. Toss it again, one or zero, and so on. That sequence is called a Bernoulli process. That's all.
And when we take the summation of these variables, IID variables, we get that is a binomial distribution.
That is a binomial distribution. Yes.
Okay, sir. And about that, sir, inter-arrival time, like x1, x2, and like that. Sir, you
Huh.
told that interval time can be described by Poisson process. So x1, x2 are
Oh, no,
those
no, no,
follow.
no, 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 no,
No,
no.
it's
I didn't say that.
geometric PMF.
Yeah, it's a geometric, right? So it's a geometric PMF. It's not Poisson. Okay.
Uh,
I just gave an example when we discuss Poisson random variable or Poisson distribution. I said this can be used to model inter-arrival or whatever the arrival process. Basically, the number of people arriving at a queue per second. That can be modeled using Poisson. Okay. People usually use Poisson to model that.
okay, sir. Okay, sir.
Okay. Yeah.
And sir, another thing
Hmm.
that's in Kullback-Leibler distance. So
Ah,
there is an exponential term with
correct.
p, curl
Correct.
p, and small p,
Hmm.
and all these things. So, sir,
Hmm.
when n is very small, like
Hmm.
our trials are very small, and
Hmm.
p tilde is not equal to p, what happens
Hmm.
then?
You'll be totally um, so essentially what you have is when p tilde is not equal to p, the Kullback-Leibler distance is large, let's say. Okay, so it's not just about that term, right? So if n is small and p tilde is not equal to p, so you should also consider the other terms, right? Square root of 1 by 2 pi n, p tilde 1 minus p tilde exponential of minus n. For example, n is 2. It will be e power minus 2 times the Kullback-Leibler. That's what you get. That is the probability. In fact, when n is equal to 2, you exactly can compute, right? Do you agree?
Sir. Yes, sir. Yes, yes.
Yeah, you have the binomial distribution. You can use that to compute, right?
Yes,
The
sir. Yes, sir.
probability. Yeah.
Yes, sir. We don't
So
need
these
that.
are all,
I
yeah,
understand.
we don't need those bounds. These
Yes,
bounds
yes,
are
yes, yes.
only asymptotics. If you have large number of trials, and if your estimate is your guess of the probability is totally off, then the probability that the sum will be equal to your guess is very small. That's what it says. Yeah, it says basically you are wrong. That's what it says when asymptotically.
Okay, sir. Okay, sir. I understand. Understand, sir.
Yeah. Any other questions? Anyone else? Anyone
Sir, another
else?
thing you asked the previous lecture,
Hmm.
like what does the definition of factorial comes? So is it from gamma function?
No, no, no. So you have the so n choose k is n factorial or n minus k factorial into k factorial, right? So if at all you want to do some approximations there, so you need to come up with upper and lower bounds, right? Right. So
Yes.
one way to come up with the upper and lower bounds is to upper bound, for example, n choose k, and lower bound n choose k, right? So how do you lower and upper bound n choose k? You need to know the upper bound on the factorial and lower bound on the factorial, right? Some n factorial you have to upper bound. So what is the upper bound? There's something known as Stirling's approximation, right? I don't know if you have heard of it.
Yes, sir.
No, sir.
Okay, so if you haven't heard, don't worry. Just
Okay.
Google about Stirling's approximation. If you want a very nice treatment of that, you can go through. Well, these are like slightly advanced textbook. So there is a book by Terence Tao on random matrix theory. Okay, so he gives a very nice explanation of these Sterlings and all that. Maybe you can just go through it. It's accessible to it's the non. You don't need to be very sound in abstract math and all that. So you can still read and understand those things.
Okay, sir.
Okay.
Okay.
Yeah.
Okay, sir.
Any other questions? Anyone else? Ayush, Jayant, Nitish, Praveen, Rishabh, Sumit.
No, sir. Actually, I
No, sir.
just trying to prove the theorem you have told.
Which one?
That, sir, the with the help of that
Sterling's.
Kullback, yeah,
Ah,
Kullback linear
ah,
divergence, sir.
ah.
Yeah,
Okay.
so first I just try to using the Stirling approximation. I just try to approximate this n factorial first,
Mm-hmm.
and then, sir, by the book they have given some steps to follow those steps, no, sir.
Mm-hmm.
So I am trying those steps only, but sir, in calculation, this estimating the n factorial,
Mm-hmm.
in somewhere I am getting something like there is a
Okay.
term called exponential of 1 upon 12n. So
Mm-hmm.
somewhere it is there, but in some PDF they just don't use that only. If they just
Okay.
taking the approximation as under root of 2n pi into n upon e to the power n,
Mm.
that much
Okay.
only.
Oh.
So there is some ambiguity, sir. Like
No,
I'm not getting
okay.
the.
Okay. So we will work it out. Maybe one of the tutorials we will see how to derive that. Even I have to work it out. I haven't proved this recently. It's been quite some time. Maybe during my PhD days I did it, but after that, no, I haven't proved this kind of problem. So I'll look at it, huh, and get back to you.
Okay, sir.
Okay. Yeah. Okay, so maybe let's get started. So today we will look at the first topic would be random variables as a function of some other random variable. So let me write that. So random variables as a function. Okay, so for example, you have a random variable x and you take a function h and operate it. So you get some, let's say, y, right? First of all, what do you mean by x being random variable? So that means it's all omega in omega. So that x of omega plus that x belongs to f for every x in R, right? Now, if you take y is also a random variable. Okay, so you can prove that whatever the properties, this belongs to f for every x in R. So you can prove this and show that y is also a random variable. Therefore, you can talk about its probability measure or a distribution for y, and subsequently you can compute the expected value and so on, right? So now suppose x has well, depending on whether it is continuous or discrete, suppose you have density if it is continuous, otherwise you have pmf px of x. Now I want to compute expected value of x. Okay, by the way, y is so if you take any function h of x, then y is always a random variable. Now particularly if h is continuous, then okay, take this as an exercise. So if h is continuous, for those who love math, if this is continuous, prove that y is a random variable. Okay, so uh, now how do you compute expected value of y? So let's assume the first case, which is discrete. So if you were to find the expected value of y, right? How do you find the expected value? Any idea?
So first we have to define the PMF of y, and then
Okay, so you have to define PMF of y, but can we not use the PMF of y and do it?
Sir, in terms
See,
of PMF of x, or
Summation or integral?
in
it's
terms of
discrete, so
expectation of x or what, sir?
in terms of its expected value of y. How do you compute? Of course, one definition is you sum over all y, as he says, PMF of y, right? This is the definition, by definition. But if you were to compute the expected value this way, you need to know what is the PMF of y. Do you agree? So how do you compute the PMF of y? What is Py of y? So you have to take the PMF of x and sum over all x such that y is h of x, right? Whenever x results in a y that I need, this y that I need, I have to compute those probabilities and add them, I get this, right? Do you agree? Do you agree with
Yes,
this?
sir.
Yes, sir.
Right? So, you can compute this, substitute and get this, but is there a different way of computing expected value of y? So, one way it would be this, right? So, y is what? H of x, right? So, given x, you have h of x, that is y. So, you have some value, right? Now, I want to see, so, okay, let me write it and then maybe you will get convinced, hopefully not confused. So is this definition make sense? Is this okay? Okay, so let's take an example. Okay, so x is, let's say, Bernoulli minus 1 1. Okay, so this is minus 1 1. This is called Rademacher random variable. So it's minus 1 1 with probability p for 1. Okay, so this is your binary random variable, right? Okay. Now I consider y to be equal to x squared. Okay, so now let's compute first what is expected value of x. Easy, right? It's summed over all x, that is x equal to, well, minus 1 and 1 x, the PMF of x, right? So this is what we have. So this is nothing but x is minus 1 with probability 1 minus p plus x is 1 with probability p. So this is so this will be 2p. So is this correct? Yeah. So pp cancels, and what is the answer here? Minus 1 plus p, which is 2p minus 1. Is this fine? This is your average.
Yes, sir.
Usual. What is expected value of y? Let's look at both ways. Overall y, okay, y, py of y. So what are the possible values of y? See, x can take minus 1 1, y is x squared, so it can take
One only.
1 only, right? Okay. Now what is the answer? So, well, you have 1. Probability of y equal to 1 is 1. So the average is 1. Right? Fine. Because it doesn't matter, you can take only one value. Let's look at the other way. So expected value of y is, I'll sum over all x, of course, in minus 1 1, h of x, which is y, which is h
So
of,
probability
which is
of
x
y
squared.
of 1 is equal to p, I think, sir. How is
Huh?
it 1? Sir? The probability of y of 1.
Huh. What is
P,
probability
P.
of y of 1? Py of 1. See, y can take only one. See, x can take either minus 1 or 1, right?
Yes, sir.
If you look at this sequence, it will be minus 1 1 1 minus 1 1 1 and so on. But if you look at the sequence y, what will happen? You will square it, right?
Yes, sir.
The moment you square it, you'll get 1 1 1 1 1 all the time. So the probability of y equal to 1 is 1. Is this fine?
Okay, sir.
Okay. Yeah. So now what is this? So minus 1 is 1, right? Minus 1 squared. Probability of x being minus 1 plus 1 is 1. Probability of x being 1. So which is 1. right? You get the same thing. So you're essentially counting the probability that x appears such that y is h of x, right? That's what you're doing. So is this clear, by the way? You just look at what all x will relate that particular y, and look at the frequency of that and multiply by the amplitude, right? That's all, h of x.
Sir,
Question?
yes, sir.
Yes.
So here y equal to x square. That's why we have -1 and 1. When you square it, we get only one value 1. So let's assume it like there is a function h which maps from one set to another set. Like I have n points in first set, and when you take a function, we get n another values in the second set. So if there is a one-to-one
let's
correspondence.
look at another. Oh, it need not be one-to-one correspondence, right? Okay, so now let me try to prove this. Let's see if I will get it. So this is, you agree with this, right? Y, y of y, right? I should look at y summation over all x such that y equal to h of x. I'm fixing y, and then py of y. Do you agree? Okay. So this I'll write summation over all y, summation over all x such that y equal to h of x, y py of, sorry, this is px of x, px of x, right? So now what is y? So I can replace y by h of x here, because y equal to h of x, right? This is clear, right? You agree? Is this fine? Is this step okay?
Yes, sir. Yes, sir.
Now, what can you say about these two summations? Fix a y, and I'm seeing all those x which got mapped to y, right? I'm summing over all possible x's. Then I will change y and see what other x's gets mapped to this y, and summing over all that. Keep on doing that. That's what I'm doing, right? For example, let me just give you. So x has, let's say, these points. Okay, y has these 3 points. For example, this gets mapped here, this gets mapped here, this gets mapped here. Okay, now this is y and this is x. Okay, and the mapping is h of x. Okay, now what is the first summation doing? So I'll fix a y. For example, I'll fix this y. Okay, if I fix y, I'm looking at all those x's which got mapped to this y, right? So what are those x's? This x and this thing, right? Do you agree? And what am I doing? I'm looking at h of this thing, which is this y, h of this, which is y, basically h of x itself. So this is nothing but h of x. I'm multiplying it by the probability of this or this occurring. Do you agree? That's what I'm doing, right? Do you agree? So in other words, I'm counting this or this for x here. Now suppose I take this as my y, the corresponding x is this, so I'm counting here. If I take this as my y, this is the corresponding x. So essentially, when I do these two summation, I'm summing over all possible x. So the claim is for all x, h of x, px of x, right? Do you agree? How do you prove this? Well, you take any x, you should be able to say that there is a y such that that x appears. So you have that summation, right? And similarly, on the other way, you pick any y here and x, look at the term and see if that term is on the right hand side. So they are both are equal. Is this fine or confusing? I think take this as a homework. I think you should go home and basically think about this again and again, so that you will get what am I saying, right? Is this okay? If you don't get it, then we'll do it in the next class again. Fine?
Okay, sir.
So if x is continuous, okay, then what happens? So expected value of y would be integral minus infinity to infinity. Instead of y, you have h of x, and you look at the density of x dx. So this is same as minus infinity to infinity y fy of y dy. See, the complication here is you need to find the density of y, which is some calculation that you need to do before computing the expected value of y. In this particular thing, you just don't need to do that. You can just directly do the compute the expected value of y. Okay, fine. Okay, so there is a different way of writing. So whether so you can write expected value of y as follows: minus infinity to infinity h of x dfx of x. So this integral, irrespective of whether so this is just a notation. Okay, so don't think that this is something. This is a notation which means that this is equal to over all x h of x px of x for discrete. For continuous, this will be minus infinity to infinity h of x fx of x dx. Okay, so this integral, anyone knows what this integral is called? This is called the Steele-Gees integral. I hope yeah, you might have heard of this, right? Yeah, so generalization of your Riemann integral. The usual integral is called Riemann. This is the Steele. Anyway, so for this particular course, don't worry about what this essentially means. It means that for discrete is the summation, for continuous this is what it is. So whenever I want to write expected value of y or expected value of x for that matter, irrespective of whether it is discrete or continuous, I can write this integral. So behind the scene, you should do the conversion. You should know that, okay, if it is discrete, it's the summation, otherwise it is other things. Okay, fine. Okay, so now let's look at a few things. For example, you know the mean, right? So what will this give us? Okay, I think we will understand some practical aspects of probability also. Suppose you go to a casino, okay, fine, and you have to. So there is a let's say somebody picks some number, okay. I'm going to say that the number that he's going to draw from is a Gaussian distribution with some mean. Okay, or let's assume that he's going to draw a sample from some random experiment. I'm going to say that the random experiment, the mean of the outcome is, or the mean of the random variable is 3. Okay, understood the problem? Okay, just to be very concrete, I go to a casino and let's say there are 100 cards. Okay, on each card you have different numbers. Okay, so that's a 1, 2, 3 till 100. He is going to pick one of them randomly. He will shuffle and pick one of them randomly. You have to guess it. Okay, so he knows, I mean, he's going to pick one of the card randomly, but there is an underlying distribution, right? Underlying probability. So for example, the probability with which he picks one is something, and so on. That's how he's going to pick. But that is something that you don't know beforehand, right? Whenever you go there, you have absolutely no clue. Okay. Now you can play the game only once, and if you win, you will get $1 million. Otherwise, you have to pay like $1 million rupees. Otherwise, you have to pay 100 rupees as a fine and come back. Okay, let's say this is the game. Now you don't know anything about the distribution, but I'll say that the mean is 50. Okay, or 70. Let's say the mean is 70. That is what I have told you. So how would you guess? What is the, this is the guessing game, right? How would you go about guessing? Remember, you don't know how he is going to pick the card. You don't know where the cards are, which card is where. He's going to randomly pick, and you don't know the distribution. The only thing that you know is, on an average, the card that he was going to pick, if you look at the expected value of x, which is 1 into probability of 1 to occur, plus 2 into probability of 2 to occur, and so on, 100 into probability of 100 to occur, turned out to be 73. So how will you guess? What is your guessing strategy?
So I will
Anyone?
guess around the mean, because mean is the center, I think, of the distribution expectation.
Not really, right? Not really. It need not be the center. Can somebody guess what is the? Can somebody tell me what is the guess? What is the best guess?
Mean itself.
Huh? Yeah, the mean itself is the guess, right? I mean, you cannot do anything. You'll just say 73. Hope that everything works fine, right? So mean is a best guess, right, in that game, right? So now, if you look at x, that is the random variable, and subtract the mean, what is this called? This is the deviation from the average, right? How much it deviates. I'll take the square of this. You can think of this as h of x, right? It's some function. I'm going to take the expected value of this. What is this called? Do you know?
Standard deviation.
Yeah, so it's this, no, it's called the variance.
Yes.
Square root of that is the standard deviation. So sigma x is the standard deviation. Sigma x squared is the variance. Okay. Everybody knows this, right? So how do you evaluate this? This is expected value of, well, okay, let's do that later. Okay. So this is the variance. Okay. Fine. Okay. We'll come back to this variance. So suppose, okay, let's look at one observation. Suppose, okay, if you look at okay, so let's come back to this later. I think I need some more, few more notions to look into this. Okay, is this fine? So the variance is something that we'll get. Okay, now suppose let's say you have two random variables x and y, okay, and they are independent. What do you mean by that? So x and y IID. What do you mean by this? X and y being IID?
Solid PDF can be written as the product of both.
Okay. So can somebody refine that? Suppose I don't know.
Expectation of xy equal to expectation of x into expectation of y.
Is that what you mean by independence?
So then probability of x given y equal to probability of x only, or the
Correct.
other way around.
But suppose x and y are continuous random variable, what do you do? See, you can define independence with respect to events, right? You know how to do that. Probability of, so A and B are independent if probability of A and B is equal to probability of A and to probability of B. All that you have to do is convert this into events, right? What is the event? X less than or equal to x for some x is an event. Y less than or equal to y is also an event. You look at the probability of that. Probability of A intersection B is probability of A times probability of B. What is this? This is fx of x. This is fy of y. This is the joint CDF, right? Right? Now, if the derivative exists, what if you take the derivative with respect to x and y, you get PDF. You take the derivative with respect to x, we get this we get. Okay. Fine. This is how you define, right? So this is the independent. So x and y are independent if this happens or this happens. Is that fine? Okay, or yes or no?
Yes.
Yes, sir.
Okay. So it's independent, identically distributed. What do you mean by that?
Same mean variance.
Yeah. No. You cannot just
Same
go by
PDF.
variance.
Same PDF.
This is equal to probability of y less than or equal to z for all z. Okay. So that means the CDF will exactly match for both. That means PDF will also match for both. The distributions match. They have the same distributions. So they are called IID. Now let's define z equal to x plus y. What do you think is the distribution of z? What do you think is the distribution of z? Can somebody tell me?
Convolution.
Now, how do you show that?
First find the CDF of Z.
Okay, so I will do it for discrete. Continuous, I'll leave it as an exercise. Okay, so let's look at discrete case. Okay, so what is so this is what I have to find, right? Right, this is nothing but probability of x plus y equal to z. Do you agree?
Yes, sir.
Now I can write this as probability of x plus y equal to z intersection y equal to some y, but I will sum it over all y. Why is this correct argument? Can anybody say? Give an explanation of why this is an equality.
Sir, how can we write this?
Right. So how can I write this?
So like an intersection.
Let me call this event as AY. Okay. What can you say? This is set, right? All those outcomes which got mapped to a number y, right? So what can you say about AY, the set AY for different y's?
It will be, sir, those
Disjoint.
Okay, disjoint. What else? Okay. Now, what can you say about this? Let's say overall y AY. What can you say about this?
So, can you tell me what is y again? AY set again?
It is all those omegas as that y equal to y. The event y equal to y is the set AY. See, I don't want to say set of all omega in omega such that y of omega equal to y all the time. So I'll just ignore everything and say y equal to y. So from now onwards. Okay. So AY is y equal to y. That's all. So what can you say about union over all y AY?
So it is any y belongs to at least any of the set.
And
What is that?
entire set.
Entire
Set.
Entire natural number or integer, positive integers.
No, right? It's omega. Don't talk about integers. This is the sample space, right? So it is all those omega in omega. So it should be omega. Is that clear, Sumit? You asked this, right? How?
Yes,
Is
sir.
this clear?
I'm just confused with the capital Y and the small y actually. That's why I'm thinking
Ah.
that it should be that this
No,
omega.
no. Capital Y is the random variable. Y is the value that I'm going to. For example, if you have random variables which can take 1, 2, 3. Okay,
Yeah, like we
I'll call it as Y.
Sets are like we define the set that x is less than y, less than equal to y.
Exactly.
Yeah,
So this means it is all those omegas such that y of omega equal to y.
yes, sir. Yeah, now it's
Y is a mapping. Okay, y, the small y is basically the number or the variable.
obviously.
Okay, so AYs are disjoint, right?
Yes.
So what I am doing, I am taking this, summing it over all this, and okay. So let me prove this. For example, see, there is an event A, okay, or let's say event B. I can write this as B intersection omega. Do you agree?
Yes.
Because B is contained in omega, so B intersection omega is B itself. Okay. I can do this
Yes, sir.
because union overall AY is omega, right? De Morgan says this is also true, right? Right? B intersection union AY is union B intersection AY, right?
Yes, sir.
So if AYs are disjoint, what can you say about B intersection AY?
Yeah, all these will be disjoint.
So by axiom, what can you say?
Sum it will be. Yes, sir.
That's what I have written here, right? Think of this event as B, this event as AI, union of AI is omega. So probability of the B intersection union of AI is what I have written here.
Okay,
And then De Morgan gives me this. Is this fine? Okay.
yes, sir.
Let's start from there, the other thing. So we have, let me just see if I have different color. Okay. Okay, so let's look at this. The maybe I'll write this here. Okay. So let me follow from here. So this is summation for all what y probability of x plus y equal to y given y equal to y into probability of y equal to y. I can write this probability of A intersection B is probability of A given B into probability of B, right?
Yes, sir.
Is this fine? So this will be probability of x equal to what did I do? So this is z, not yeah, z, right? I can write this as z minus y given y equal to y, right? Because given y equal to y, I can substitute small y for capital Y. What is this? See, y and x are independent, right? IID. Because of IID, I can write that A given B when A and B are independent is equal to A itself.
Yeah.
Okay. What is this? This is the PMF of X at Z minus Y. This is the PMF of Z. This is called what? Convolution, right? Px of X convolved with Py of Y. This is the definition for convolution. So now, if X is continuous, if X and Y are continuous, what can you say about Fz of Z? This is minus infinity to infinity. You should look at Fx of Z minus Y, Fy of Y, Py. So this is also convolution, right? The key thing here is, if you look at the proof, IID, well, more than IID, it should be independent, okay? I don't need IID, so independence. I'll just write independent. Okay, is this fine?
Yes, sir.
Easy, right? So that means if you have two random variables independent, if you sum them, the resulting random variable will be the convolution of the two. Right? I'm talking about the distribution. Okay, fine.
Yes. Sir, one
Okay,
question.
now,
Sir, actually, I
go
heard
ahead,
about
go ahead.
convolution. No, sir. But sir, what does it actually mean, sir? Convolution, sir.
So what does it mean, right? Can you somebody from electrical engineering want to describe what convolution is? I can tell you. Okay. Okay. So okay, how do I put it? Okay, so let's say you have a car. Okay, I'll write the car as a box.
Okay, sir.
You understand, right?
Yes.
Especially, this is your suspension of the car. You know what a suspension is, right? Suspension is your shock absorbers, okay, of your cycle or car, whatever it is, right? So now, what is the output? Output is how much. So suppose you run over a hump, right? Of course, the wheel will go up and down and all that. How much you go up and down is the output, right? Input is what? Hump. Output is how much uncomfortable are you, right? So how much up and down you go, right? Your seat goes, right? Right. So now if I want to characterize this, it turns out that, for example, I give you a very sharp bump, okay? It's an impulse. You know what an impulse is, right?
Yes.
Sudden bump, okay? I will see what will be the response. So suddenly this will also go up and then come down, right?
Yes.
This is how the response is used. Suddenly you also go up, not much, but you slowly come down, right? It goes up and down. That's the shock absorber, right?
Yes.
You agree?
Yes.
Now, this is given to you, but I have a very nice road, but so once in a while there is a bump like this. Okay, this is my road. So if I take my car in this road, what will be my response, right? How will the seat go up and down, or how will I go up and down? How do you calculate this? Maybe I'll put this as 0. Okay, something like this. See, I can write this as some small impulses. Okay, I can write any function h of x as what? H of t delta of t minus x, right? dt. You agree?
Yes.
You know what impulse is, right? It's a functional, right? Okay, so this is what you have, and you have a series of impulses, and I know the response for each impulse. So if I want to know the response of this entire thing, what should I do? I should add these things with some different scaling, right? So that results in what is known as convolution. Okay. Okay. So maybe I'll give a few homework problem wherein you compute the convolution of two things, two functions or two PDFs. Okay. Think of this, right? So you have this convolved with, let's say, maybe this itself. This is T1, this is T2. Just try to convolve these two, okay? Height is 1. What will be the convolution? Okay, just think about this, you'll probably get the answer. Okay, so let's look at another thing. So for example, let x1, x2, etc. be random variables. Then what can you say about expected value of x1 plus x2 plus and so on, xn? What can you say about this? Well, strictly speaking, this is what you have to do, right? So integral n integrals x1 plus x2 plus and so on xn. If it is a continuous random variable, you look at joint density dx1 through dxn, right? It turns out that this is equal to sum over all expected value of xn. Okay, check. I won't prove this, it's very easy, straightforward. Everyone knows how to derive this, right? Is it not?
Which one, sir?
Nitish. Yeah, Sumit, you are saying something?
Yeah, sir. The expectation you have written this one, sir.
So expectation of the sum is the sum of the expectations. That's what I have written. So in other words, expectation is linear.
Yes, sir.
Okay.
Yes.
You just have to check this. This is not a difficult thing to do. Nitesh, is this clear?
Yeah, yeah.
So we can prove it just by the definition you have written. No, sir. Just we have to take that density function to the each of x1, x2, and
Correct. Yeah. So, but the thing is, density function, you won't be able to integrate it with respect to x1 for the first term, because you have x1 times fx1 through xn of x1 through xn. So, but you can integrate the density function with respect to x2 till xn. So, and then use the property that integral, for example, integral fxy of dy is fx of x, right? If you
Yeah.
integrate with respect to one variable, that variable will vanish. So use that here. Okay.
Okay, sir.
Okay. So let's look at a few other things. So now we know what is. Let's go back to variance. Expected value of. Okay. This is sigma. X squared is expected value of x minus expected value of x squared. This is nothing but expected value of x squared plus expected value of x whole squared minus 2 times expected value of x. So this is nothing but expected value of x squared plus expected value of x whole squared minus 2 times expected value of x times expected value of x. This is a constant. So expected value of alpha x is alpha times expected value of x. Okay, that's because the integral is linear. So this is whole squared. So this is expected value of x squared minus expected value of x whole squared. You remember this, okay? Fine. Everyone knows this, right?
Yes.
So the variance is the second moment minus the mean square. You subtract the mean square from the second moment. That is the variance. Okay. Now let x1, x2, etc., xn be independent random variables with variances sigma let's call it a sigma 1 through sigma 1 squared, sigma 2 squared, and so on, sigma n squared. Then what can you say about variance of x1 through x1 plus x2 plus and so on xn? Can somebody tell me?
The summation of those.
Yeah, so it will be summation, right? This happens only if they are independent. Okay, if they are not independent, then this is not true. Okay. For example, let's look at the extreme case. X2 is equal to x1 with probability 1. X3 is equal to x2 with probability 1, and so on. So if you sum them, the variance will be equal to the variance of the first one, right? So it won't be. So the variance won't change much. Do you agree?
Yes, sir.
Yeah. Right. So that's what this is. Okay. Any questions so far?
No, sir.
Okay. Now. Okay. So now. Suppose, okay, let's understand few things. I think this will be a repetition for Ayush Agarwal, but let me do this because I want you to understand this. Suppose I say the mean of the random variable is 0. Okay, what can you say about the PDF or the PMF? What can you say about the PMF or PDF? Yes. Ayush, can you tell me? Ayush. Yes, go ahead.
Is it like some values are positive and some values are
No,
negative?
I'm asking Ayush. So
Okay.
I hope he's not sleeping. Hello? Ayush? Okay, he seems to be sleeping. Mic not working. Okay, fine. I'm just joking. So, Rishabh, you can go ahead.
Sir, so expectation is 0. So maybe some values are positive and some are negative. So when you're multiplying with the probability,
That is correct. Yeah, that is correct. But can you refine it further? Sumit?
So it is symmetric. So it must be symmetric.
Correct, right? So the PDF should be symmetric. That means the positives and the negatives are the same, right? So I mean equal weightage. The PDF or PMF will be symmetric. Okay. Now suppose it's not equal to 0. Okay, so now implies symmetric distribution. Okay. Suppose expected value of x is not equal to 0. So what does that mean? The entire so I can see one thing. So basically it's either shifted towards right, the PDF or PMF shifted to the positive or negative, or it's like skewed towards positive or negative. Okay. Now you take x minus expected value of x. What do you get? I've subtracted out the mean. So what is the mean of expected value of x minus expected value of x?
0.
0.
0, right?
Yes.
Yeah. So that means the distribution of this is symmetric, right? I mean PDF, right? This new random variable.
Yes,
Okay.
sir.
Now if I take squared and take the expected value, it gives you the variance.
Yes.
Suppose I take cube. Okay. I look at this. So what are the possibilities now? This can be equal to 0, greater than 0, less than 0. Let's see what can you infer from equal to 0. If it is equal to 0, again, what can you conclude? Yes. What can you conclude?
So it should be the symmetric.
Symmetric.
Again, symmetric, right? What if it's greater than 0? What can you say? What can you conclude?
It is shifted towards the right side. Little bit.
Right. So if it is less than 0, what can you say?
Towards left side, shifting toward the left.
Yeah, so, right. So that's the information that the cube is giving, right? So in other words, the PDF, this is the mean expected value of x. If this is the case, it will be positive, right? On the other hand, this is the case, it will be negative, right?
Yes. Yes.
This is the case, it is 0, right? So it's giving us some information about the distribution, right? What about fourth moment? Expected value of x minus expected value of x whole power 4.
Yeah, with less than equality case, I think it will be set.
No, you cannot have less than or equal to. It's fourth power, right? It's always positive.
Either 0 or greater
Right.
than. Yeah.
It will be equal to 0 or greater than or equal to 0. 0 is like trivial. Greater than or equal to greater than 0 is what we look at. What about fifth moment?
These three possibilities will be there. Sir.
Again three possibilities,
Yes.
but it will tell you something more. Okay, so let me give you an example and stop probably today, but maybe next class you can see. Okay, so now I have sorry. Suppose I want a random variable whose distribution is how do I put it? So the fifth. Okay, let me just look at this. So this is my random variable. Okay, so it can take 1 and minus 1. Okay, so the probability that it takes 1. Okay, so let me just use delta, and this is 1 minus delta, right? That's the probability, right? So what is the mean of this random variable? Mean is definitely something, right? So delta it's 2 delta minus 1, right? That's the mean. So variance will be something. So the point is, if you want to know, if you want to describe this distribution, right? What is it that I need? I need delta. So that means if I know expected value of x, which is I know that 2 delta minus 1. So this implies delta is 1 plus expected value of x by 2. So mean will describe what delta is. The moment you know delta, you know the distribution. You are done, right? For example, you have let's say okay, so this example, okay. Okay, this is some density function, right, of continuous random variable. So if I need to know this, so what is this? The mean of this, it's a plus b by 2. That's the mean, right?
Yes, sir.
Okay. Now, if I know the mean, I know a plus b by 2. That means I know a plus b, but I don't know a and b, right? That's not enough information.
Yeah.
If I compute the variance, I want you to compute the variance for this in the by next class, variance. And the moment you compute the variance, you will perhaps with the mean, you can see what a and b are, right? So that means you need both mean and variance to characterize this. Now, you can similarly have very complicated distributions, right? Some very complicated distributions wherein only mean and variance will not suffice. You may have to have third moment, fourth moment, fifth moment, and so on, maybe 100 moments. If you know all 100 moments, maybe you'll know what the PDF is, right? So in other words, moments will give us a lot of, these are called moments, okay? Second central moment is called variance. Third central moment is this. This is the third central moment. If I put fourth power is fourth central moment, and so on. Okay. So these moments will give me a lot of information about the distribution.
So, did you just made a statement that if the mean is 0, the PDF is symmetric, right?
Yes.
So you mean symmetric about the y-axis?
Yes.
Okay, so then if you have a random variable which takes the value -3 with probability 1 by 4 and one with a probability 3 by 4, its mean is 0, right?
I'm sorry. Yeah, I'll
But
take that.
it's not symmetric.
Yeah. I'm sorry. I'll take that. Yeah. So you're right. So you're saying maybe one. I think you should mute man. It's very hard to speak otherwise. Okay, so for example, -2, right? This is let's say some delta. This is 1 minus delta. I can always pick -2 delta plus 1 minus delta. I want this to be 0. So 1 minus 3 delta is 0. So this means delta is 1 by 3, right? Is that correct?
Yeah. That's what I did. I constructed this problem lesson.
Yeah. So that means, I'm sorry, it's not, you cannot say that it is symmetric around 0, right? So what about the third moment? Okay, that's what I was about to say. So if the third moment is 0, what can you say? So this is incorrect, right? This is not correct. I'm sorry. I should not have done this thing. It says nothing much you can say. So essentially, on an average, you'll observe 0. That's what it says. So what if the third moment is 0? Can you say that it's equally on both sides?
It'll just be a cubic equation. The roots of that cubic equation should be 0. But then again, you can argue that you construct something like this.
Can you mute? It's very hard for me to speak. So so what essentially happens is, so the point that I would like to make is, if I know, for example, the higher moments, I can describe what the function is, what the distribution is, by just looking at, for example, various moments. The third central moment, if it is 0, that means hey, wait, let me just check.
So to be symmetric, sir, we can say if the mean, median, and mode of the distributions are same, we can say the distribution is symmetric.
Sorry, what is that? If the mean, median, and mode is?
If all are same, then we can say the distribution is symmetric. Like, sir, take the Gaussian distribution. If the mean, median, and mode are same, then they both, three of them lie in the middle point. So we say that the distribution is symmetric, I think.
I have to think about that. So essentially, it's the other way is true. So if it is symmetric around y-axis, then definitely mean is 0. If mean is 0, doesn't mean that it should be symmetric. Okay. Right?
Yes, sir.
Okay.
Will it hold for continuous also? Yeah, it's continuous also, it holds good.
It need not be symmetric. So essentially the weightage on an average on positive and negative are same. So equally likely, right? If you look at, for example, third moment, what it says, so if third moment is negative, that means this is a bigger impulse here, okay? Because this has more weightage. And you take the cube and then it gives us some information about what are the negative values that occurs with what probability, right? So that when you combine them, it's more negatively dominated than positively dominated. Okay, so I think I'll give a precise example, so which will tell me some information about the distribution. Okay, like this. Okay, in the next class. I'm sorry about this. This is a big goof up. So thanks, Savan, for catching this. Expected value of x is 0. It doesn't mean that it's symmetric. Symmetric means expected value of x is 0. Okay. Any questions, confusion? Any questions?
No, sir.
Hmm?
No, sir.
No, sir.
So actually, if the when you raise a random variable is symmetric, then the expectation will be 0, no, sir.
Yes, yes, yeah.
But the converse is not true, no, sir.
Converse is not true. So in fact, if the distribution is symmetric, the first moment, that is the mean, is 0. The third central moment is 0. The third moment is 0. Fifth moment is 0, and so on. All the odd moments will be 0.
Okay, sir.
Okay. Yeah. Okay. Okay. Any other question? No.
No, sir.
Okay. Nitish said sound not clear. You can hear now, or you missed something, Nitish? Nitish? Okay. If there are
Now
no
clear,
questions, then
sir.
we'll stop.
Now
Yeah.
clear out.
Huh?
Hello.
Now clear. Okay. So you had any question?
Okay.
Okay. If there are no questions, I'll stop here. Next class, maybe we can spend some time initially to clarify some doubts. I have a meeting now at 5, exactly at 5. So I'll take off. Huh? Next class we will meet again, and then you can drop in an email, upload in Piazza, whatever. So we will try to clarify.